Hi, how you doing? It's Glenn here with the Beers Law Lab. I'm just having a nice summer here with my virtual labs. Hope you're having a nice summer there too. Let me just show you how to get in here. Click on that link in the assignment page and you'll see the concentration lab. This is something that you've already done. So we'll go to the Beers Law Lab. This is HTML5, so that means this particular virtual lab will work on your tablet also, be it iOS, Android, whatever you like to play. Now let's play around here. The reason why you should play around is because that's the assignment. That's part one of the assignment. It is to explore the controls. I see there's a control here. There's a little light here. Let me turn on this flashlight. Ooh, it's green. Ooh, look, it goes through this container of liquid. Oh, look, I can change the length. I can change the width of this container of liquid, and as I do so, the percent transmittance of the light through the liquid changes. If I have a narrower container, more light gets through. A wider container, less light gets through. What about absorbance? This absorbance is quite low. As I decrease the width of the container, the absorbance gets even lower. So, it looks like absorbance means the amount of light that the liquid absorbs. And transmittance means the amount of light that the liquid transmits. The amount of light that the liquid lets through. Let me just test that hypothesis using some other chemical here. Let me just make this real concentrated. Wow, that's only 2% transmittance. So if I let this light go through less of the liquid, I should get more. Yes, more transmittance. More transmittance. If I put this tool right in front of the lamp so that there's no liquid obstructing the path of the light, I should get 100% transmittance. Let's see if that's true. Oh, it is true. I should get 0 absorbance. Oh, it is true. So it is true then that absorbance means the amount of light that got absorbed by the liquid, and transmittance means the amount of light that got through the liquid. But is this light always going to be green? Let me see. Ooh, I can make this light whatever color I want. Fascinating. Ooh, now look at this. This is interesting. It looks like this material is purple, and I'm getting a lot of Ooh, wait. Where is it one? Ah, right there. Wow, that's weird. So this color can't get through this purple material. Now that must be because this material is purple. I mean, when light goes through this liquid, all of the other wavelengths get absorbed, but purple gets transmitted. But this green is very different from purple, so it must be getting absorbed. Wow, look at that absorbance. A whole number. Alright, so this is fun. Let's have a look at these chemicals. Ooh, look. Cobalt nitrate, cobalt chloride. The first part is the same. I'm not sure if you're going to remember this from your naming compounds exercises of the lecture section, but these are all ionic compounds because they begin with a metal: potassium, copper, nickel, potassium, cobalt. These are all metals, and they end with nonmetals: nitrate, chloride, dichromate. Oh, okay, well, dichromate contains a metal, but it also contains a nonmetal, oxygen. Oh, you could see it in this formula here. That oxygen right there, the chlorine, the oxygen, the sulfur, the oxygen. Right, so compounds like that, which contain metals and nonmetals, are usually ionic compounds composed of a cation, or a positive side, and an anion, or a negative side. So the first word is the cation. Second word is the anion part. So these are different chemicals, all ionic compounds with cations: cobalt, potassium, nickel, or copper, and then various anions: nitrate, chloride, dichromate, chromate. There's another chloride here, that's interesting. Sulfate, permanganate. And then there's this drink mix. Drink mix, of course, is not an ionic compound. It's just drink mix, mostly sugar, some food coloring in there, some artificial flavors, maybe some natural flavors if you got the good stuff, right? Maybe some vitamin C in there, right? So, you should play around with all these tools here. This is a nice little ruler that measures the path length, the length of the path that this light has to travel through, getting absorbed a little bit all the while. This double arrow, as you saw, changes the size of the container, so therefore changing the path length. This ruler just measures that path length for you. Here, let me show you something kind of cool. So right now the transmittance, the absorbance is about 2, right? Path length is 1 centimeter. You go closer, still 2. Software doesn't care until you get into the liquid. Now it's not 2, but watch. Let me make the path length exactly half a centimeter. So I'm going to cut that path length from 1, where the absorbance was 2, to a half. Right there. You see that? A half. Ooh, look, 1. Aha! So if I cut the path length in half, I also cut the absorbance in half by transmittance. If I double the path length out to 1 here, transmittance drops by a lot. Okay, so this is about 1% out here. Let's see the transmittance in here. This is like 10%. This is like 9%. Oh, okay, so that's weird. The transmittance drops by a factor of 10. This is 9. This is 0.9 something. And this is 9 point something. This is 9.5. This is 0.95. So transmittance drops by a factor of 10. However, as you saw, the absorbance only changed by a factor of 2. Well, isn't that interesting? Okay. Now, I'm not saying that's important for this activity. I'm just saying that's kind of cool. So, let's see. Back to the assignment. Explore the controls. Well, I've done that, and you can do that in your own way. I mean, there are many different controls here. Some controls that I haven't tried. You should try them all. I can press this. Ooh, that's a reset button. How about that? And this is the concentration. The mm, that means millimolar, or millimoles per liter, or 0.001 moles per liter. So yeah, have a good time playing with that. And let me advance to number 2 here. Can the cation affect the color? Okay, how are you going to figure that out? Well, I just told you what cations were, just in case you forgot from the lecture portion of the course where you named compounds. Now, how are you going to figure out if cations can change the color? Well, I have a suggestion. Find 2 or more chemicals that have the same cation. For example, cobalt. Cobalt nitrate, cobalt chloride, they have the same cation, cobalt. See if they are different colors in the lab. And don't stop there, because they might be an outlier. You want to test this question out on as many chemicals as you can. So look at this potassium dichromate and potassium chromate. They have the same cation. Are they the same color? What about this potassium permanganate? Same cation as these guys. Are they the same color? Does the cation change the color? Is that going to help you to figure that out? Well, you might also need to test the anion. Because what if it's both the cation and the anion that is affecting the color, right? Let's try to find some chemicals that have the same anion. Here's some. Nickel chloride, cobalt chloride. Now they have different cations, but they have the same anion. So if the anion is responsible for the color, in the case of cobalt chloride and nickel chloride, then they should be the same color because the anion is the same. I could see that they're not the same color. So it must be the case in this particular example, cobalt chloride and nickel chloride, it must be the case that the anion is not responsible for the color. So that's the way, this is the portion of the lab that you should use to figure out the answers for number 2 and 3. It's this solution portion, this tool right here. You know, you pick these things, and you can test out what colors they are, and if it helps you, you know, you can test your absorbance, because the absorbance is actually also color dependent. But you know, you figure out the way that makes sense for you, and then answer these questions in an accurate fashion. Cation and anion. Now, a beverage company is having some trouble. The color of the drink mix is supposed to be light red, 0.8 molar, but that's not always the case. What is going on? What if the color intensity is too low? It is too pale. What does this mean? So let's go back to the lab. We're talking about drink mix. What can you do here to make the color intensity too low? What can you do to make this a very faint pink? Well, I mean, nothing I do here changes the color of the liquid, but something that I do here does change the color. And what am I doing here, right? You do it, you figure out what you just did, what you changed, and then you write the answer here. Like, what is it that controls color intensity? What about solution color? What is it that controls the color right here of this solution in here? Okay, not this. Yeah, not this, not that. Just this. What controls this color, right? And then the solution started out with the correct color intensity, but over time it became dark. Nothing was added to the vat. Okay. So now that is a problem that you just have to use your imagination for, because it says over time the appearance changed to becoming darker. And the text here says that the stuff became darker. It doesn't say that the color was different. It says the color intensity was different. It's not like it used to be red and now it's blue. No, it used to be light red and now it's dark red. You see, it says it's supposed to be light red. It's supposed to be light red, and then the solution started out with the correct color intensity, so light red. But over time it became darker, so what happened? Now, there is nothing in here that allows you to cause the software to make time go by. You know, I could sit here all day long and nothing is going to happen to this color. But there is something that you can do to make this color darker. Well, I guess not right now. Well, I guess that's a little bit darker right there. But suppose it started out like this. You can just move the concentration slider to make this darker. But now what would be doing that in nature? Use your imagination. Use your experience from everyday life. What in nature changes the concentration? What in nature, if you do not add anything to this container of liquid, what is it in nature that will cause the concentration to increase over time? I'll let you mull that over during this nice summer. Explore the controls. I think you've already done that, right? Okay. A spectrometer measures, yes. You should read this. That indicates to you that this whole setup here, this is the spectrometer right there, and this is the light source. But this is not just pretend, folks. This is a real life tool. This is just a simplified, software gamified version of a real life tool. This liquid, it could be blood plasma, you know, it could be urine samples, you know, and when you check off lab tests to be done for your patient's body fluids, some of those lab tests might be using a spectrometer like this one. Much more complicated, but the same in principle as this one, whereby light of some preset wavelength, or some wavelength that determines, that is determined by the lab technician or the chemical test designer. Some light gets passed through your patient's blood plasma or your patient's urine or whatever. looking for the concentration of a particular chemical. Maybe, I don't know, whatever chemical it is that you and your doctor are interested in quantifying in your patient's body. So yeah, this is a true tool that is used today. It's called a UV vis spectrometer because the light source is capable usually of wavelengths in the visible light range, as you see here, but then also further down beyond the purple here to the ultraviolet range. And there are a lot of more expensive tools that can go deep into the ultraviolet range, such as 200 nanometers. Whereas this tool in the virtual in the simulation can only go down to 380 nanometers. So anyways, I'll let you spend some time with that paragraph there to understand what this is all about. And now you're going to want to answer these questions here. When it says where, or when I ask you where, what I mean is where in the length of the path. I mean, is it at this point? Or is it at this point in the middle of the liquid container? Or behind the liquid container with respect to the light source? Or in front of the liquid container with respect to the light source? So that's what I mean by where. Where is the green light most intense? Where is the green light least intense? Where is the intensity of the light changing? You can notice that the intensity of the light is not changing back here. I'm getting 0.03 absorbance the whole time I'm back here, as long as I'm capturing the light. Also, up here, I'm getting 0 absorbance the whole time. Any position over here. So this is what I'm asking you to do and to answer. This is number 7. Investigate the intensity of the green light passing through. Okay, so here I want you to graph. Okay, I don't want you to sketch the graph. I want you to actually plot accurate points. Okay, there are many ways to do that. My favorite way is Plotly, but hey, you might like Microsoft Excel, or you might like the Open Office spreadsheet. I think it's called Calc or something. You use whatever graphing software you like. I'm going to use Plotly just to show you. I'll probably have to stop this video soon because it's running kind of long, but I'll continue on another one. Yeah, I better stop it right now, and then I'll continue the other one with the Plotly.